In this example, we need to find each x value at which function is discontinuous. So our goal is to find the x value where the function is discontinuous, and if at that if any location where the function is discontinuous, then at that x value, then we need to determine, okay, if it is discontinuous, we still need to see whether it is continuous from the right or continuous from the left or neither. So these are the things we need to check. So what type of function we have given, let's try to look into that. You can see over here, this is actually the piecewise defined function. When we see the piecewise defined function, I actually personally like to write down the information on a real line. What I mean is, I want to summarize this information on the real line. Let's try to do that. Okay, so let me draw the real line over here from negative infinity to positive infinity, and then let's try to look back into the function and then try to determine the partition number over here, and 0 and 1, those are the number I see over here, right? So where you can see the rules are like the set of rules are like a different, right? From when the x is less than 0, the rule is x plus 3. When it is between 0 and 1, it is 3x squared, and then so on. So based on that, I want to just divide this real line between, let's say, from negative infinity to 0, 0 to 1, and 1 to infinity. Okay, so when I do that, let's try to see here. So it says that when x is less than 0, when you choose any real number which is less than 0, then we are going to use this rule, x plus 3, right, to find the value of the function. So if that is the case, let's write that down over here. The function here is x plus 3, right, when it is less than 0. So let me have the parenthesis over there. When it is equal to 0, and then greater than 0, right, and then less than 0 or less than or equal to less than 1 or less than or equal to 1, then the function is defined by 3x squared, right? So if it is between 0 and 1, including the endpoints, because of those equal sign. So that's why I have those bracket there. So let me just write down the function is defined as 3x squared. And when x is greater than 1, right, so the function is defined as 3 minus x. So let me write that down over here. I like these summary of these information on the real line, so that it's easy for me to later on look into where the function is. Let's say what is the left side limit, right side limit, how the function behave from the left, right, so on. So it's very easy to look into that. Okay, all right, so let's try to look into this summary over here. You can see here the rule here is x plus 3, and then that would works for any real number when you choose from negative infinity to 0. Forget about for a moment exactly at these endpoints, but if you neglect those endpoints over here, either on this interval or over here, we know over here the function is x plus 3, and then 3x squared, 3 minus x. All of these are polynomial function, and we know that the polynomial functions are continuous on its domain, right? So if that is the case, x plus 3, if it is defined over here, definitely it is continuous. And then over here, any real number between 0 and 1, it is continuous, and then 3 minus x is continuous. I'm asking you to wait for a moment at the endpoints, because at the endpoints, you can see here when we go closer and closer to 0 from the left and right, these two different functions are behaving. So we need to look into that, how the function behave, right? So we need to look into that. But if we forget for a moment those endpoints, it's clear that this function x plus this function f of x, whose rule is x plus 3 over here from negative infinity to 0, 0, and then 3x squared on 0 to 1, and 3 minus x on 1 to infinity. These are polynomial functions, so definitely it will be continuous on those interval. So let's try to summarize that fact, and then we'll look into after that at these partition number or the endpoints. Okay, we'll look into that. But before that, it's clear by this by using the fact that polynomial functions are continuous on its domain. This given function f is actually continuous on where to where, negative infinity to 0. I'm excluding these partition numbers, right? So that endpoint of 0, and then from 0 to 1, right, and then 1 to infinity, and the function is definitely continuous. What is the reason of that? Because it is those function is polynomial over there, right? Okay, so if that is the case, we are done with those, but we have only two things left over. We need to check at x equal to 0 how the function is behave, and at x equal to 1. We have not looked into that so far, and at x equal to 1. But it's good that among all of those infinitely many real number, we just now look into only two locations, at x equal to 0 and at x equal to 1. Okay, so let's try to see into those locations. So how do you check any function is continuous at any number or not? We use the definition of the continuity, which is we just need to check a limit of the function if that is equal to the value of the function or not. But even to check that, we need to make sure that if the limit exists, right? So if that is the case, why don't we just look into the limit of the function at 0? But to do that, let me just find first what is the limit of the function at 0 from the left side. Let's find the limit of the function at 0 from the left side. That means I need to go closer and closer to 0 from the left side. So let me go closer and closer to 0 from the left side. But when I go closer and closer to 0 from the left side, the rule on the left side is defined by x plus 3. So if that is the case, I just need to look into how the x plus 3 function behave when x gets closer and closer to 0 from the left side. But since x plus 3 is a polynomial, by using the direct substitution property, we saw the behavior of the function is like this. X plus 3 just approaches to 3 when x gets closer and closer to 0 from the left side. In the same way, let me go closer and closer to 0 from the right side, and then when I go closer and closer to 0 from the right side, right at 0, you can see the function is 3x square, right? That's how the function behave. So we need to look into that fact. So if that is the case, let's try to compute the limit of the function at 0 from the right side. So like we have discussed recently, on the right side of 0, the rule is defined by 3x square nearby 0, right? The function is always defined by 3x square. So if that is the case, we just need to check how 3x square function behave when x gets closer and closer to 0 from the right side. But 3x square is polynomial, so by the direct substitution property, we know how 3x square behaves. How that behaves, well, we just need to check, we use the direct substitution property, and then this gives us value 0. Wow, okay. The left side limit we have obtained here, the left side limit of this function we have obtained is 3. The right side limit at the 0 we have obtained, that is 0. So if that is the case, they are not same, right? 3 is not equal to 0, right? So that's what we get. So if that is the case, what can we conclude based on this fact over here? Limit of the function at 0 does not exist. Wow, what a nice information. And we know that if the limit does not exist, then function is not continuous, right? So this implies f is not continuous, or we can say f is discontinuous at x equal to 0. Right? But the question here is, okay, we figure out at least one value where the function is discontinuous, right? So okay, no problem, we figure out x value, but we also need to figure out either at that location whether the function is continuous from the right or left or neither. How can we check that? Well, we just need to compute one more thing, the value of the function exactly at 0. So how the value of the function at 0, or what is the value of the function at 0? Exactly at 0, if you look into here, the value of the function exactly at 0 is defined by, because we have this bracket over here, or you could look into the original problem over here, it's given by this rule, 3x square is the rule. That's how it's defined, right? So if that is the case, we need to use that rule to find the value of the function at 0. So 3 times 0 square will be equal to then just 0, and which is equal to the right side limit here, right? So the right side limit. So if that is the case, since the right side limit of the function is equal to the value of the function, then actually it's so since this is equal to the right side limit of the function, let me write that fact over here, right? We can conclude that f is actually continuous from the right. Continuous from right at x equal to 0. This is the fact we have obtained at 0. Okay, so it is discontinuous at 0 because the limit does not exist, right? But since the right side limit is actually equal to the value of the function, we can say it is continuous from right. Okay, let's try to check the similar type of thing over here at x equal to 1. What do we need to do? Well, we just need to check either limit of the function at 1 equal to the value of the function. To do that, we need to find the left side limit if that is equal to the right side limit to conclude if the limit exists or not, right? So let's go closer and closer to 1 from the left side, and you know that when I go closer and closer to 1 from the left side, the function is what was the function, how the function behave by this rule 3x square, right? So if that is the case, let's do that. So limit of the function when x gets closer and closer to 1 from the left side is actually behave like how the function 3x square behave from the left side, but 3x square is polynomial. By using the direct substitution property, we just get that is 3. In a similar way, let's go closer and closer to 1 from the right side. When we do that, 3 minus x is the rule, right? That's how the function is defined. So if that is the case, we can just see how the function 3 minus x behave when x gets closer and closer to 1 from the right side, which is again by its polynomial. By using the direct substitution property, we just get that is 2. Wow, this is 3, that is 2. So the left side limit is not equal to the right side limit. So right, so if that is the case, we can say that limit of the function x approaches to 1 does not exist. So if that is the case, what can we conclude? Then again, f is discontinuous. If the limit does not exist, how will you be able to compare with the value of the function, right? So there is no way to do that. So add x equal to 1. All right, but still again we need to, okay, it is discontinuous at 1, but we still need to see if it is continuous from the right or left. To do that, let me just check what is the value of the function at 1, and let me go back to the problem. At 1, because of this bracket, or you can see over here, the function is actually defined by 3x square, that rule, right? So because of that, let's use that over here, that rule, to find the value of the function at 1, and which is 3. And this is exactly equal to the which limit over here? The left side limit. So since it is equal to the left side limit of the function, right? Left side limit of the function at 1, the value of the function is equal to that, and then we can say, although it is discontinuous, but f is continuous from the left. Continuous from left at x equal to 1. Okay, as a summary, you might have realized to check the discontinuity of the function, we need to check either limit of the function is equal to the value of the function or not. But to check the limit of the function, we need to find if the left side limit is equal to the right side limit or not. If the left side limit is not equal to the right side limit, then the limit does not exist, then the function is discontinuous. But to check either it is continuous from the left or right, we can still check if the left side limit is at least equal to the value of the function or not, right? So if those are not same, then of course then maybe it is neither right continuous, neither continuous from the right nor continuous from the left. But if one of the limit, let's say left side limit or right side limit, if that is equal to the value of the function, then it will be continuous from the right or left, depending on which limit is that equal to the value of the function.